Let's take a look at the next example, still in 7.5, which is verifying the identity tangent of theta equals 1 minus cosine 2 theta divided by the sine of 2 theta. Again, generally speaking, the guide rule we want to kind of follow whenever you're trying to verify an identity is try to work with the more complicated side first and turn it into the other side, simply because you have a lot more things you can kind of do. The left-hand side is just a simple trig function tangent of theta. There's not much to do there. Let's focus on the right-hand side, which is that 1 minus cosine of 2 theta divided by the sine of 2 theta. Both of these kind of jump out as being double angle functions, so the double angle identity should come into play. In the denominator, we've learned that the sine of 2 theta is equal to 2 sine theta cosine theta. We also want to use a double angle identity for the cosine of 2 theta. Now we know that we have 3 different ones to choose from. We can either do cosine squared theta minus sine squared theta, 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. In terms of choosing which one might work best here, we have that first term of 1 minus, so it would be kind of nice if we could get like that constant to kind of cancel out. And we can do that if we use the particular identity for cosine of 2 theta, that cosine 2 theta is equal to 1 minus 2 sine squared theta. Once we substitute that identity in, when we remove the parentheses by distributing, we get 1 minus 1, and then this is going to become a plus 2 sine squared theta, all divided by 2 times the sine of theta times the cosine of theta. And that's good for us because the positive 1 and the negative 1 cancel, and that leaves us with 2 sine squared theta all divided by 2 sine theta cosine theta. And now we're able to cancel some common factors. The 2's cancel. We can cancel 1 power of sine in the numerator with 1 power of sine in the denominator, leaving us with sine theta over cosine theta, and we know that that is the quotient identity for the tangent of theta, which is what we were trying to show. So this has verified the identity. Again, one of the things that I'm trying to warn everybody with in class is, when you see me work through these problems, it's pretty straightforward. Start all the way down to the end without making mistakes. If you try a different identity or try one of the other forms of the cosine of 2 theta, you can still verify the identity and get the correct answer. It just might involve a little bit more work, or it might take you to a place where you get stuck. Again, the thing with these verifications is don't be squeamish. If something doesn't work, take it as far as you can, and then maybe back up and try one of the other forms to see if maybe you have better success or maybe an easier time working with one of the alternative forms. But again, kind of the motivation for that particular selection for the formula for cosine of 2 theta is by using that one, we get the constants to cancel, and we're able to work more directly with the trig functions. The next set of formulas we're going to look at are the half angle formulas for tangent. There's actually 2 different ones we could use. The tangent of alpha divided by 2 is equal to 1 minus cosine of alpha divided by sine alpha. And the tangent of alpha divided by 2 is also equal to sine of alpha divided by 1 plus cosine alpha. Let's take a look at example 7. We have the tangent of alpha divided by 2 is equal to the cosecant of alpha minus the cotangent of alpha. So it's kind of, again, there's more than one way to verify these. You could choose whichever side you want to. Again, noticing the alpha over 2, it's always probably a good idea if you have multiple or half angles to kind of get rid of them first. Here we have a choice in terms of which formula I want to use for the tangent of alpha over 2. Again, ask yourself the question, how are these 2 sides of the equation similar? How are they different? Well, obviously, the left-hand side has an alpha divided by 2. The right-hand side just has the angle alpha. So I probably want to make a choice for the tangent of alpha over 2. I either have the first formula or the second formula. Once I pick one, I then need to kind of show that that's going to be equal to the cosecant of alpha minus the cotangent of alpha. And one of the things that I kind of realized is that that right-hand side has a subtraction sign in it. So too does this first formula out of the bunch. Furthermore, that right-hand side has two functions, and if I choose the first formula, I can actually create two functions by splitting apart that numerator. And so that leads me to the choice that I probably want to use this formula out of the two for substituting out the tangent of alpha divided by 2. So where I see tangent of alpha over 2, I can put this as 1 minus the cosine of alpha divided by 2 from our new half angle formula for the tangent. Excuse me, not divided by 2, divided by sine of alpha. My mistake. From there, I can create two terms, just like I have on the right-hand side, by splitting apart the numerator. We can write this as 1 divided by the sine of alpha minus the cosine of alpha divided by the sine of alpha. And now from some of our more basic identities, 1 divided by sine alpha, that's the reciprocal identity for the cosecant of alpha. And cosine alpha divided by sine alpha, that is the quotient identity for the cotangent of alpha. And that's exactly what we were hoping to verify. So just to kind of highlight some of the formulas that we've come across up to this point, we've looked at sum and difference formulas for both sine, cosine, and the tangent. We've seen the double angle formulas for sine, cosine, and tangent of 2 theta, keeping in mind that when it comes to the cosine of 2 theta, we have 3 different versions we can use. Cosine of 2 theta is equal to cosine squared minus theta minus sine squared theta, or it's equal to 2 cosine squared theta minus 1, or it's even equal to 1 minus 2 sine squared theta. We have the power reducing formulas for sine squared, cosine squared, and tangent squared that allow us to take those functions that are raised to a power greater than 1 and write them in terms of only trig functions raised to the first power, albeit of double angles. And then we also have our brand new half angle formulas for sine, cosine, and tangent, where those plus minus signs are determined based upon the quadrant of alpha divided by 2. The next set of formulas we're going to look at are the product to sum formulas. Kind of as the name implies, they allow us to go from the product of 2 trig functions to either a sum or difference, as it may be, of 2 trig functions. Let's just kind of investigate the first one. If we have the sine of alpha times the sine of beta, this can be rewritten as 1/2 times the expression cosine alpha minus beta minus cosine alpha plus beta, where the difference is on the left-hand side, we have the multiplication of 2 trig functions, whereas on the right-hand side, we have essentially a sum. It's just a sum of 2 terms where one happens to have a negative coefficient. But either way you slice it, on the right-hand side, it's either addition or subtraction, not a multiplication that's involved. Let's take a look at example 8. They ask us to express each of the following functions as either a product or a sum. As a product, as a sum or difference. Here we have the sine of 8x times the sine of 3x. This is the product of the sine of 2 functions. So we're going to use that first identity that we just mentioned. According to our formula, this should be equal to 1/2 times the quantity. It's the cosine of alpha, which is the first angle. That's 8x minus beta, which is the second angle, which is 3x. Subtracting the cosine of the first angle, which is 8x, that's alpha, plus beta, which is the second angle, which is 3x. From here, the only thing we would want to do is simplify those arguments that are inside the cosines. This is going to become the cosine of 5x minus the cosine of 11x. And there you have it. Starting with a product of 2 sines, we've changed it into a difference of 2 cosines with a factor of 1/2 out in front. Let's take a look at the next one. This is the sine of 4x times the cosine of x. So if we have sine times cosine, we're going to be using this formula here. According to what we have, this is going to be 1/2 times the quantity, the sine of the sum of the two angles. That should be 4x plus x plus, see if I can squeeze it in here, the sine of the difference of the two angles. That's going to be 4x minus x. Okay, the only thing from there you'd want to do is simplify the arguments of the trig function sine. This would become the sine of 4 plus 1 is 5x, plus the sine of 4x minus x is 3x.